This is a short introduction to our course on analysing sporting performance. I'm Adrian Oldner and I work with Tony Houghton at the Centre for Innovation in Technological Education in Cambridge. And I'm doing a little introduction showing some of the history of the technology and the science and the maths that we're going to introduce you to. The area generally is called kinematics, putting things in motion, and there's the Leaning Tower of Pisa. One of the big problems that many people tried to work on was to predict the position of the planets, quite important in religion. And that involves a number of particularly important ideas. You've got to be able to observe things carefully, you've got to be able to collect some data, you've got to be able to do some calculations on that. You need to come up with some ideas, some theories, to try to make some general rules, and also, if possible, see if you can find reasons why they work. So, for example, one of the early Renaissance leaps forward was by Copernicus in Poland, and he made the big change that he proposed that the planets moved around the Sun rather than around the Earth, which was the prevailing view up until that time. The important thing for astronomers was to be able to have a good, accurate means of keeping time, and Tycho Brahe, just before the new inventions of telescopes, made very, very careful observations of the planets, and he was able to come up with some ideas really based still upon the idea that things moved around in circles. It was about the early 1600s that the work in optics really leapt forward and allowed people to make the early telescopes. But at the same time, Galileo Galilei in Venice had been working on all sorts of things to do with gravitation, and when he learnt about the new telescopes he had to get one, and very quickly came up with an idea to improve it, and with that he was able to recognise some planets of Jupiter. The German astronomer Kepler took the measurements from Tycho Brahe, and he came up with the idea that rather than use circles, it was an egg-shaped kind of curve that the planets followed, and that's known in maths as an ellipse, and he thought that this would be true for all planets. But it took a mathematical genius, Newton, the British guy, allegedly to have an apple drop on his head, to come up with the mathematical theory that an ellipse would be the answer if the force of attraction between the Sun and the planet was proportional to the square of the distance. So basically, the further away, the very much weaker the force gets. So F equals k upon r squared. The Royal Society was a very important move forward in England because it enabled scientists, not just in England but all over the world, to communicate together and to share ideas. There was a famous spat between Isaac Newton and Robert Hooke for who actually came up with the idea of the inverse square law, but basically at any rate that meant that the results were written down and published and scrutinised by other scientists. But it wasn't for quite a while later that actually a proper experimental confirmation was done of the inverse square law. It remained a mathematical idea, a model. Another important step forward that Newton was involved in England, and at the same time a contemporary Leibniz was working on in Germany, was to come up with a mathematical system which enabled you to describe rates of change, what we now call the differential calculus. They use different kinds of symbols and they use different words, but basically at the same time they arrived independently at a system. Leibniz wasn't just a pure mathematician by any means. He believed that calculation wasn't a great clever trick, and if you could get machines to do it for you, that would save a lot of work and make sure things were more accurate. And he was made a Fellow of the Royal Society for his invention of a mechanical calculator, a more sophisticated version of the one which Pascal had come up with in France somewhat earlier. That kind of calculating machine led to the phenomenal work of Charles Babbage, assisted by Ada Lovelace, who came up with the first computer programming system, and they designed a mechanical machine now in the Science Museum called the Difference Engine, and that also inspired the work of Alan Turing during the war, a code breaker at Bletchley, and after the war built one of our very first valve-driven electronic computers in Teddington near London. So really, we've come a long way in terms of technology and our understanding of the world, thanks to science and mathematics, but also thanks to technology. So now you can use a phone and a camera, and you pick up satellite transmissions, and we can find out enormous distances and pick up wonderful photographs from the Hubble telescope. But do we know how these things work? So in our analysis of sporting performance, we'll use this modern technology, but underneath we're still standing on the shoulders of those giants we've just been talking about, who enabled us to land on the moon and watch satellite TV. It's not rocket science, but it certainly could be, and I hope you'll get plenty out of the course that you're now going to follow.